Hey guys, this is Chapter 9, Part C, studying MO theory. We just finished talking about valence bond theory, now we're moving to molecular orbitals. It's a more in-depth description of how bonding occurs. It's also a very different approach. When I shift from valence bond theory to MO theory, I kind of compare it to the shift from if we start out learning about capitalism, where when we study molecules with valence bond theory, we study one atom at a time, and it's like, okay, every atom, we look at the electrons it has, we think about, okay, well that atom wants to do the best it can with what it has, so it's kind of an every atom for himself kind of approach. That's the capitalism side. When we go to MO theory, we take a more holistic approach, and with communism we say, okay, well, it's not about what each atom wants or needs to do, it's more about the good of the molecule. So in communism, it's about the good of the country or the good of the state, and everything has to be done and distributed just the right way to make the state better. So with MO theory, we're going to take all the electrons and orbitals, and instead of assigning them to specific atoms, we're going to throw them all in a pot and say, okay, let's decide the best way to distribute everything. Okay? So I often start out with an example. Let's just say when my wife and I got married, if we got married and let's say we both had Ford Taurus cars. In that case, the Ford Taurus is a good sized sedan car. If I have 4 or 5 people, we can ride comfortably in it. But there's 2 issues, like, every day to go drive my Ford Taurus, it doesn't necessarily get the best gas mileage. So it's kind of expensive to drive 40, 50 miles a day in that car. That's bad. And then also, let's just say when I want to take my kids out to the park and they want to bring 4 or 5 of their buddies with them, a Ford Taurus won't carry as many cars as like a Chevy Suburban or something like that. So if my wife and I get married and we both have Ford Tauruses, that doesn't really make sense anymore. It was fine when we were by ourselves, but once we got married, we might make the economical decision to say, okay, let's trade both of our cars in and say, let's get rid of these 2 Ford Tauruses, which are kind of mid-sized vehicles. We'll trade them in and say, let's get a Honda Civic and let's get a Chevy Suburban. And basically by doing that, we're going to be able to take better care of our family and save more money in the long run. Now, how does that work? Well, as much as we can, if it's just me or my wife and I going out for a drive, every chance we get, we're just going to use the Honda Civic. Why would we do that? Well, every time we drive the Honda Civic, we're saving money. Whether we have a Ford Taurus or a Chevy Suburban, when I drive my Honda Civic, I'm going to use less gas, I'm going to save more money, it's more energy efficient. Okay? On the other hand, let's just say that my wife and I are taking our kids and some of their friends out and we need to have 7 or 8 people in the car. That's when we'll get the Chevy Suburban out of the driveway and go take it. We only use that high cost vehicle when we have to. Okay? We know that we don't want to use it, but it's there if we need it, and if we have to use it, we will. Okay? So the approach to molecular orbital theory is kind of the same idea. So if we start out looking at, let me give you a little background first. So the idea is we're going to take atomic orbitals. So if I have 2 atoms that are going to bond, each atom shows up with certain orbitals. We're going to throw them all together and say, okay, forget the atomic orbitals we showed up with. Let's trade those in and get molecular orbitals that make more sense for us. Okay, so we're going to change atomic orbitals to molecular orbitals. Now, when we do that, we're basically going to have to add the orbitals together. And if you've had any physics, we talk about light travels as a particle and a wave, that kind of thing. When 2 waves interact with each other, if the 2 waves are moving in phase with each other, when you add them together, they actually enhance each other. That's called constructive interference. If the 2 waves are out of phase, where when one's going up, the other one's going down, when you add them together, they actually kind of reduce each other. That's called destructive interference. Okay, so when we take orbitals and add them to each other, which is what we're doing in this theory, you can have 2 possibilities whenever you add them together. If they add together in phase, they get constructive interference, which is good, and you can add them together and get destructive interference, which is bad. you're going to get both things happen. So every time I add two orbitals together, I'm going to get a new orbital that results from destructive interference, which bad means the energy is going to go up, or I can add them together to get constructive interference where the energy goes down. And remember, we're talking about stability of atoms, so going down in energy is good, going up in energy is bad. So we combine our orbitals, we add them together. Instead of having atomic orbitals, they're molecular orbitals. If we combine 2 atomic orbitals, we get 2 molecular orbitals. If we combine 8 atomic orbitals, we get 8 molecular orbitals. So we're always going to conserve the number of orbitals that we put together. So if I look at the hydrogen atom, okay, the hydrogen molecule, H2, I look at the orbitals and say, okay, well, hydrogen's in the first row, so the only orbital it has is a 1s orbital. But when I put the hydrogens together, one hydrogen is here, he shows up with an s orbital. The other hydrogen also shows up with an s orbital. When we combine them, so when the atoms come together and overlap, we're going to get 2 molecular orbitals from the addition of those. Okay? When I add them together, if they're in phase with each other, which when they're the same color, that means they're in phase, they're going to add constructively, and it's going to give me a lower energy molecular orbital. So they combine, I get 1 orbital over the 2 atoms. That's constructive interference, that's good. The energy goes down. But what if the orbitals are not in phase with each other? That's represented by the opposite colors. Now they actually destroy each other anywhere they overlap. So I actually end up with, right in the middle, there's actually a gap here. There's a plane where electrons can't cross through. It's a region of 0 probability of finding an electron. That's called a node, N-O-D-E. That's bad. If we're wanting to share electrons and we got a place in the middle saying electrons can't pass through, that's not a good thing. So that's going to be my destructive interference. It's going to have a higher energy. So these are my 2 molecular orbitals. I combine 2 atomic orbitals. When I combine them, I got 1 good combination, 1 bad combination. We're going to name these We're going to name these. I don't have it both on here. The good one is called a bonding orbital. The bad one is called an anti-bonding molecular orbital. So bonding is down, anti-bonding is up from where I started. Okay, and that's always going to be true. If the energy of the molecular orbital goes down from my starting point, that's a bonding orbital. It means if I put electrons in those orbitals, I'm saving energy. If I put electrons in that orbital up there, I'm losing energy. Okay, so, and then the gap, again, MO theory does have mathematics behind it. From the atoms by themselves, if I put electrons down in the bottom, the energy change corresponds to, in chapter 8, when we learned about bond dissociation energies, the energy difference between here and here actually corresponds to the amount of energy it takes to break a bond. Meaning, if I have an H2 molecule, here's where the electrons are. If I want to break the bond, I have to put the electrons back up in the atomic orbitals. That difference is the amount of energy that would have to be put in. So, for hydrogen, H2, 1 electron came from this atom, 1 electron came from this atom. When we put them together, the middle shows my new orbitals that I need to put the electrons into. So on the sides are the atomic orbitals. That's what I had when they came together. But once I form the molecular orbitals in the middle, I now need to put the electrons in those orbitals. So the bottom one, this is 1 orbital right here. So the line is just where I can put my electrons in. I can put 2 electrons in this orbital just like we always have. Again, it's 1 up, 1 down. They have to have opposite spin. So I put 1 electron from this guy, 1 electron from this guy. They both fit in here. As long as it's just 2 electrons, that's the only place I have to put the electrons in. I don't have any more, but if I had a 3rd and 4th electron, they would have to go up into the anti-bonding orbital. And basically what that would do, right now I'm saving a lot of energy by putting them down here. If I had to put electrons up there, then I end up costing myself the same amount of energy, because the amount that this goes down should always be equal to the amount that that one goes up. So if I put electrons in both, then basically there's no benefit to forming these orbitals in the first place. So we combine the atomic orbitals to form molecular orbitals. We always maintain the number, and when we split them, it's always going to be one with two orbitals overlapping. One's going to be lower in energy, one's going to be higher. And we call the lower one bonding and the higher one's anti-bonding. Once we start filling them up, we're following the same rules we always have. We fill from the bottom up. We can put 2 electrons in each orbital. If we have several orbitals at the same level, we'll put 1 in each before we start pairing them up. So for the hydrogen atom, or excuse me, hydrogen molecule, that is the structure. We can also calculate one more thing, the bond order, which when we started learning Lewis dot structures and resonance, we did calculate bond order in that section. We had an approach where we looked at how many different bonds there were being shared in different places. We had kind of an equation to type into. We're calculating the same thing here, but it's a very different approach. Okay? Here we're building this schematic and we're going to use the electrons in different orbitals. We're going to calculate the bond order in a different way, but still, if the bond order is a 1, that means a single bond. If the bond order is a 2, that means it's a double bond. If it's a bond order of 3, that means a triple bond. Okay, so the bond order is the same thing, but it's a very different way to come about it. So the way we calculate bond order, if we're doing MO theory, is that we're going to do the bond order equals 1/2 the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. Okay, so for the hydrogen molecule, if I look back, and we'll look back in a second, here's how it's going to plug in. It's really simple. The half in the front is easy. This number is the number of electrons in bonding orbitals. And then this number is the number of electrons in anti-bonding orbitals. So let's look back just to confirm that. So in this schematic, how many electrons, and I'm focusing in the middle here, only in the middle, how many electrons went into bonding orbitals? These 2. Those 2 electrons are in the bonding orbital. How many electrons do we put in the anti-bonding orbital? There's none up there. So that's 0. So 2 in bonding, 0 in anti-bonding. So that's where our numbers came for the equation to plug in. If I do 1/2 of 2 minus 0, that's a bond order of 1. What that means is, in an H2 molecule, there will be a single bond. If we drew the Lewis dot structure for hydrogen, you'd have an H and an H, and you put a line between them, and that's it. We already knew that, but this is another way to determine it. Now, if we look at helium, helium is also in the first row of the periodic table. So we still just have 1s orbitals on both atoms. So the 1s here, the 1s here, they overlap. I get a constructive and a destructive. The schematic looks the same. Okay? But this time, the number of electrons, the first helium atom has 2 electrons, because helium normally has 2 protons and 2 electrons, right? The other helium atom also has 2 electrons. So when we put them together, we make our molecular orbitals in the middle, and then we have 4 electrons that we have to deal with. So I have to say, okay, what am I going to do with my 4 electrons? Well, I start at the bottom and I work my way up, just like normal. The first 2 electrons go here, that orbital's full. Then the 3rd and 4th electrons have to go up there, and I fill that one up. Luckily, I don't have any more electrons, because if I did, I ran out of orbitals, okay? But for hydrogen and helium, you can't ever have more than 4, so that's all you're going to get. Okay? But I have 4 electrons. This is my schematic. What's the bond order? Well, it's going to be 1/2 of the number of electrons in bonding is 2. The number of electrons in anti-bonding is also 2. So it's going to be 1/2 of 2 minus 2. Go to the next slide. The bond order between 2 helium atoms is 0, which means 2 helium atoms won't make a bond. there's no benefit. They don't save any energy. Remember, helium atoms are happy the way they are. If you start trying to make them bond, it makes them worse, not better. Okay, so the He2 molecule doesn't exist. Now, oxygen, the O2 molecule, this is going to demonstrate, like when you look at the hydrogen molecule and you're like, why do we go through all this? It may make you kind of question what the importance of MO theory is. Okay, so I'm almost out of time. I'll finish this intro. If I look at this structure for the Lewis dot structure of oxygen, O2, how many unpaired electrons are there? You look at that and say, well, the electrons and the bonds are paired because there's one electron from each atom overlapping. So that's a pair of bonding electrons. That's a pair of bonding electrons. This is a lone pair, lone pair, lone pair, lone pair. It looks like all the electrons are paired up. But we know that if a molecule has all the electrons paired up, that molecule, there's a word called diamagnetic. Diamagnetic molecules are unaffected by a magnet. So if I have oxygen, I can cool it down and turn it into a liquid. If I bring a magnet up to that liquid, it shouldn't be affected by a magnet at all. If this is correct, which everything we learned in Lewis dot structures and valence bond theory says this is correct, but it's not. The oxygen liquid is affected by a magnet. If you bring a magnet up to oxygen liquid, you can make it move and dance and all kinds of stuff. So this structure is insufficient. It proves that valence bond theory is not as good as we thought it was. So in the next video, we're going to do MO theory and see how we know that there actually are unpaired electrons in that molecule.